Hello, this is Jim Corkins, and we're continuing on with 2.3, and this is the application of electric fields and electric forces. So it's a combination of everything that we've been doing up until this point. So everything from 1.0 all the way to now. If you haven't done the reading, please do so. The chapters are listed here for whatever textbook that you have. If you have OpenStax, and you're in Physics 131, please read Chapter 5. If you have Night, please read Chapter 26. If you are in Physics 101 or Physics 112 and you have OpenStax, that'll be Chapter 18 or Survey Chapter 15. If you have the Coletta textbook, and that applies to everything, then please read Chapter 17 for whatever course that you're in, 101, 112, or 131. Again, this is also related to Homework 3. If you're in my Physics 131 course, and also Homework 3 on Physics 112. Let's get started. So, how does electric fields and forces become unified? Well, what we found out earlier is this, that to find the basic electric field, you could take, if you're given a force equation right here, to find the electric field at that point, you would just divide out the other point charge that was creating the force. So, for example, up here, suppose you have a point charge, let's say Q, a point charge right here, Q1, and that's creating an electric field in all directions, right? Actually, hold on. I'm sorry. This would be where the electric field is. So let's suppose you had a negative charge right here, and you wanted to measure the electric field at this point, right? But there was a positive charge sitting here, okay? So also, let's say you knew the force of attraction between these two things. And that force would be K, and you have your negative Q, and your positive Q is causing your force, divided by their distance apart, R, which is being squared, right? So, right here, this from here to here, they're separated by a distance R, right? Well, if you wanted to find the electric field due to the negative Q at that point P, which is a distance R away, let's not worry about that right here. So this is a distance R separated right here, between the two charges. Right? But this is also the point P where you're measuring the electric field. So if you wanted to find the electric field at point P due to this negative Q, and you knew the force generated between those two things, to get the electric field due to that negative Q at that point P, right here, you would simply have to take whatever force that you had and divide out the positive Q that is sitting on top of point P. So in other words, to get the electric field due to that negative Q at where the positive charge is sitting at point P, you would leave the negative Q in the equation, and then I'm going to take the R squared here and the point positive Q. You would be effectively taking that out, essentially getting negative Q over R squared. So that sounds awfully simplistic and reductionist, right? So and that's really how hard it is. That's the most difficult this gets. To unify the electric field and force, if you're given the force equation, just go ahead and divide out if you wanted to find, if you knew So you have two charges and you wanted to find the electric field at this point where one of the charges is sitting at. We'll just divide out that charge that's causing the force, and that'll give you the electric field due to the other charge, right? Counter to that too, right? Let's say you're given an electric field. Okay, let's say you're given the electric field at that point, and that electric field would be written as K times a negative Q, and this is the electric field at point P, over R squared. And you wanted to get the force. Well, the force due to a positive Q interacting with that electric field, right? Well, now you just multiply that into it, and then what you get is the negative Q and the positive Q all over their distance part squared. And so this is a great tool to use, because if you're given a force and you wanted to find the electric field, piece of cake, just take out the other charge that's causing the force, and then you have the electric field at that point where the positive Q was sitting at. If you have the electric field at that point and you wanted to figure out what the force would be on a charge sitting at that point, you just multiply that charge by that electric field, and that gives you the mutual force between those two charges. That's essentially what this is saying here, as well as right here. Okay? Again, if you have a charge right here, charge A, which is creating an electric field, right? At this point right up here, well, and you wanted to find the force on that charge B, you would just multiply that B charge by that electric field due to the A charge, and then you would have their force, right, between the A and B charge. If you had the force between the A and B charge and you wanted to find just what the electric field for that A charge is at that point, you just you divide out the B charge. Pretty simple, okay? Well, let's do some application problems, okay? So, suppose this is usually when we are taking into account F equals QE, it's due to a capacitor, okay? So, if you're ever given a homogeneous electric field like this, right here, okay, the only way you could calculate the electric field is if you know the force acting on a test charge in that homogeneous electric field, okay? That's the only way to do it. You can't calculate, there's billions of, this is the positive plate right here. So imagine you have a positive plate. How do I know that's positive? Well, it's billions of positive charges are built up here, and the electric field is pointed away from them. And that positive plate on the capacitor is going to in turn create billions of negative charges built up on the other plate, okay? So now you have a homogeneous electric field, and let's call that homogeneous electric field with the letter E, okay? Well, how do we find out what that electric field magnitude is, right? If the electric field is the same at any point in here, the only way for us to find out the magnitude of that electric field is to place a charge in that electric field and then measure the acceleration on that charge. Suppose we would know the mass, but we'd also know the charge on it. We place that charge, a known charge and a known mass, in that electric field, and then we would see an acceleration come about. And then that mass times that acceleration is the force, and that would then in turn allow us to divide out. To get the electric field, you take the mass times the acceleration on that charge and divide it by the charge, and that gives you the electric field. Okay? And the electric field is going to be measured in newtons per coulomb. So if you ever see, again, we talked about that earlier, but the electric field is going to be represented in a newton per coulomb. Okay? So that's how you would measure a homogeneous electric field in a capacitor, is by placing a test charge in that area and then measuring its acceleration. And you would have to know the mass and charge on that test charge. And the resulting acceleration you could use to give you the magnitude of the electric field. Okay. The counterpart is also important to this as well. Okay. Suppose you knew the magnitude of that electric field, and let's say the magnitude of that electric field is 2 newtons per coulomb. Well, if you place a test charge in there, okay, and that test charge is negative 9.3 microcoulombs, well, to measure the force on that force is going to be equal to charge times that electric field magnitude, which is going to be, this is, you have to put the absolute value around this stuff, right? Because we're going to want the magnitude, not the direction. So that'll be negative 9.3 times 10 to the negative 6 coulombs times 2 newtons per coulomb. And that gives you, multiplying those two things together, that'll give us 18.3 times 10 to the negative 6 newtons. So that's how much force would be generated on this test charge in an electric field of 2 newtons per coulomb. Okay? So that's the uses that we typically use electric field for, all right? With the force is equal to Q times E, typically what we do is we are applying this to a homogeneous electric field like one generated by a capacitor. Okay? But let's make sure you get the concept of this down right. So let's do some active learning problems like in your tutorial. Okay? And in this tutorial, we're going to be placing charges in a homogeneous electric field, and also some electric fields also which may be going outwards, like those generated from a single point charge. So we're going to be placing charges in homogeneous electric fields, but also electric fields that are not homogeneous, which drop off and get weaker the further out they go. Okay? But we're going to be applying this kind of concept to it, right? And just to remind you that if you place a negative charge in a downward pointed homogeneous electric field, that negative charge is going to move opposite the direction of the electric field. Okay? And that is because that negative charge is moving towards the positives and away from the negatives. Okay? So this downward pointed electric field is created by a capacitor, and the vectors pointed down are pointed away from the positive plate and towards the negative plate. So if you place a negative charge in that electric field, it's going to move towards that positive plate. All right? If, like in the last problem, if you place a positive charge in that electric field, it's going to move towards the negative plate, which is going to be downstream. So what I feel is that an electric field is a stream of water moving from positive to negative. So a negative charge is going to move opposite that direction. A positive charge is going to move in the same direction as the electric field. Okay? So that's another big concept. Okay? And essentially, it would be like this. If you threw a positive if you threw a tennis ball into a stream of water, you would expect that tennis ball to be moving downstream. Well, that's the same thing as a positive charge. The weird part is, if you threw a tennis ball in a stream of water and it starts moving upstream, Well, that would be really weird, but that's what a negative charge does. It moves opposite the stream of the electric field. Okay? We'll get into more about the stream and which way charges move when we talk about voltage and also electric potential energy. So, voltage, electric potential, but also electric potential energy. All right. The cool thing too is if you have an electric dipole, the dipole will actually begin to spin and twist and rotate, right? Because the positive part is trying to move in the direction of the electric field. The negative part is trying to move in the opposite direction of the electric field. So what happens is if you had, I suppose I should draw it, an electric field pointed up and a negative charge was right here and a positive charge is right here, and they're broken by a really strong bond, this negative charge is going to be moving down and the positive charge is going to be moving up. So this is what's going to happen first, this is what's going to happen second, and this is what's going to happen third. So it's going to begin rotating until it swings back and forth. If there's any friction, it'll end up coming to a stop, and what will happen is a force is going to try to pull the positive part and separate it from the negative part. And if that force of separation is greater than the bond between these two things, then it'll break that valence bond, and the electric field can actually be used to pull atoms apart and actually pull the electrons off of the nucleus. So it's another cool application of a homogeneous electric field. You place atoms in that electric field, and you can watch them twist and turn. Okay. So the big takeaway from this is that negative charges will move opposite the stream. If so, the electric field is pointed down, the negative charge is going to move upstream, and it's because it's moving towards the positive plate and away from the negative plate. Positive charge will move downstream. So if I place a positive charge right here, a force is going to be generated on it, and it's going to move downstream. Okay? So now we know the consequence of placing charges in a homogeneous electric field, and then how to use use this equation to actually calculate. If you're given two of these, then you could calculate the third, right? So if you want to find the force, you have to be given Q and E. If you want to find E, you have to be given the force and Q. So now you know how to quantify it and also the result of charges placed in an electric field. Okay. Well, let's do some tutorial problems. All right. This is 2.3 Electric Fields and Forces tutorial. And this is going to be I think it's the first page of that tutorial. And this is going to be B and F. And I chose B and F because they're very different from each other, right? And so what you're supposed to do in this is you're given a description, and you're supposed to draw the direction of the electric field, okay? That would be causing this description, okay? And it'll be a constant electric field like that caused, homogeneous electric field like that caused by a capacitor. So, for example, in this problem, right here, you have a negative charge speeding up while moving in a straight line. So basically they're saying this: you have a negative charge, and that negative charge is going to be speeding up, right? Which means it's going to have an acceleration vector in the same direction due to while it's moving in a straight line. So definition of speeding up again is you have your acceleration vector and velocity vectors are pointed in the same direction. So let's say that acceleration vector is this big. Well, what that means is that you have also then you'll have a force moving it in that direction of that acceleration vector, correct? And so if you have a force moving it in the direction of that acceleration vector, well, what we learned last time right here is if a force is driving this electron up, that's caused by a downward pointed electric field. And since it's only moving in a straight line, that means this electric field has to be pointed opposite the direction that it's moving, right? So an electric field is going to be moving. So a negative charge is going to be moving opposite the flow of the electric field. Okay? And opposite the direction of the force. So that electric field is going to be pointing up and to the left. Okay? So that's what you're supposed to do in this, right? So what I did, how I do this, is I read the description and I define speeding up, slowing down, constant velocity. Speeding up, again, is going to be where your velocity vector so I'm going to draw a bunch of velocity vectors. I'm going to define these right here. If your velocity vector is pointed in the same direction if your velocity vector is pointing in the same direction as your acceleration vector, then that is speeding up. So this is going to be speeding up, and this is also going to be speeding up. Okay? Speeding up. So if you have a positive velocity vector and a positive acceleration vector, that is speeding up. If you have a negative velocity vector and negative acceleration vector, that is also speeding up in a straight line. If you have an acceleration vector opposite the direction of your velocity vector, that is called slowing down. So the second group right here, this group, when you have a positive velocity vector and negative acceleration vector, that is slowing down. And if you have a negative velocity vector and positive acceleration vector, that is also slowing down. Over here, if you have a negative velocity vector and zero acceleration, that is constant velocity. And if you have a positive velocity vector and zero acceleration, that is also constant velocity. That is going to come into play right here in 2.3. So in this case, we have an object that is speeding up at the instant that is shown, but it is turning to the west. That means if the top of the page is north, never eat sour and watermelons, that means it's going to be turning to the west. Okay, so let's think about this. That means it's going to have two acceleration vectors. If it's speeding up and it's got a negative velocity vector, that means it's going to have an acceleration vector that is also down. But if it's turning to the west, that means it's also going to have an acceleration vector pushing it to the west, right? And this is a positive particle. So I'm going to put these two acceleration vectors together. I have an acceleration vector that is pointing down, so it'd be speeding up, and then another acceleration vector that is pointing in the negative x direction. Okay, so I have a negative y direction acceleration vector and negative x direction acceleration. So the overall acceleration vector started here, ended here. So the net acceleration vector is going to be pointed down and to the left. Okay? And that means that there must be a force. I'm going to use green for the force. That is also overall down and to the left. So I must have an overall force that is down and to the left. What that means is, since an electron always flows downstream, or a proton rather always flows downstream, that means it's flowing in the direction of the force. That means the electric field must also be pointed down and to the left. Okay? So whenever an object is turning, you've got to draw an acceleration vector in the direction that it's turning. In this case, west is to the left. So you would have an acceleration vector pointed to the left. Okay? But speeding up, you have another separate acceleration vector that is in charge of speeding up, slowing it down in the direction that its velocity vector is pointed, or opposite that. Okay? And then I put those two combination acceleration vectors together to get a net acceleration vector by doing vector addition. The net acceleration vector would be the resultant or hypotenuse of those two. And I use that to create my force vector, which is the green vector. And that then tells me the direction that this electric field must be pointed, because a positive particle is going to be moving downstream in the direction of the electric field, in the direction of the force vector. Notice that an electron is moving in the direction of the force vector. That's because the electric field is pointed opposite that, right? Again, that means there must be a line of positives on the top right side for this guy, and a line of negatives over here. All right? So this is a really cool way for you to conceptualize the integration of forces and electric fields on a conceptual level. Let's move on to the other page. In the other page, you're supposed to take a look at this picture and make a description and write what this particle should be doing. Okay? So this is the second page of this. And so right here, you're given a description and you have to write the electric field. Here, you're given the electric field and you have to write the description. So go ahead and, based on what we just learned, go ahead and try to answer, describe what would be happening here. Okay? And to do that, I suggest that you draw your force vector and your acceleration vector. So in the instance that you see this picture, which way would the acceleration vector be, or force vector be pointed, and thus which way would the acceleration vector be pointed? And combining that acceleration vector with this velocity vector, that should tell you what this object should be doing. Okay, so try this one right here. Okay, we're back. Well, let me go ahead and draw this. Well, this is a positive particle, so there is going to be a force vector pointed downstream, right? And if there's a force vector pointed downstream, that means there's going to also be an acceleration vector in that direction. So I'm going to tag that acceleration vector onto this velocity vector. And essentially what I'm imagining is this acceleration vector is turning this velocity vector. And so since this velocity vector does not have another acceleration vector up or down, this force vector is only to the left, and that means the acceleration vector is only going to be to the left. That means this velocity vector is neither going to be speeding up nor slowing down, but this acceleration vector is going to be turning this to the left of the page, or west. and it's going to be traveling at a constant, I'm going to say constant speed. Not constant velocity, but speed. So it's going to turn it to the left, and also it's going to keep it traveling at a constant speed. Okay, as it's doing that. So it's not going to be speeding up nor slowing down at this instant. And that's because the acceleration vector is perpendicular to the velocity vector. All right. So you're supposed to describe which way it's moving, but also what is it doing, speeding up, slowing down, or constant speed. Okay? So there we go. Why don't you try this next one? Okay? So take a moment, pause the video, and try this one for yourself. Okay. Well, this electric field is going to create a force in the direction of the electric field. Okay, this is a positive particle again, so a force is going to be created in that direction. Okay, and that means you're going to have an acceleration vector also in that direction. Okay, and that acceleration vector is going to be here. Actually, I'm going to tag it on to this, right? So if the velocity vector, so I'm going to create, actually, I think I was right the first time. Let's just tag on that acceleration vector right here. I'm going to add that acceleration vector to the velocity vector. So that's going to cause two things to happen, I'm guessing, right? It's going to be, so let's break this up. I'm going to break up this velocity vector into the direction of the electric field, okay? And this is just the way I see it. But that velocity vector is it's pointing to the right, okay? Which means it's pointing down and to the right. And I'm trying to align the velocity vector in terms of this electric field. Okay? So the velocity vector actually has two components. So this is the direction of the overall net velocity vector. But that velocity vector has two components. One pointed down and one pointed up and to the right. And if you look at it, our acceleration vector, okay, is actually going to be pointed opposite its velocity vector, okay? But that acceleration vector is going to be pointed in that direction, but it's also pointed, that overall acceleration vector too, and that's a net acceleration vector, is going to be serving to slow it down in the straight line, but also going to be causing it to spin or turn. So I'm guessing that since this acceleration vector is tagged on to this velocity vector right here, that it's going to turn it, and I'm going to say it's going to turn it, this direction must be counterclockwise, while this was clockwise to the west. This is turning it, it's going to pull it and turn it counterclockwise. But since the inline acceleration vector is pointed opposite the velocity vector, it's going to also serve to slow it down at the same time. And this is counterclockwise right here. So it's turning counterclockwise, or I could say it's turning kind of northwestish at this moment. But at the same time, it's also slowing down. Okay? The third part of this page has to do with, has actually two parts to it. It has to do with describing the motion Actually, this is part of the lab. This is part of a lab, and this is the other part of the lab. So in that lab, the left part columns are you're supposed to describe what is happening at each one of these points, and the right part is you have the description, and now you have to write what the electric field is. Okay? Okay, so here we go. Notice this is interesting. This left one is that this electric field is going from being weak. So notice the electric field is really far apart here, and then it seems to be the electric field line density is getting closer and closer and closer, right? And then over here at C, so I'm going to say this is high density, and I should use blue to describe the electric field. So electric field has a high density, and over here it's going, so the high density is, I should actually say increasing density. And then it hits a point, and then from down here it seems to be decreasing in density. So what does that mean? Well, it means the electric field means to be getting stronger. E is increasing in strength. Well, here the electric field is decreasing in strength. So if the electric field lines are increasing in density, then that means increasing in density, means it's getting stronger. The electric field is increasing strength. Which means it's increasing, the force is increasing. And that means the acceleration is increasing. So if the electric field lines are increasing in density, that means the electric field is increasing in strength, which means the force on this positive particle is going to be increasing, and that the acceleration must be increasing. So I guess here's what I'm saying is that this guy right here at A is going to be speeding up. And you're only supposed to write speeding up, slowing down, constant speed. So I'm saying that this is speeding up at point A, because from A to B, it is increasing in the electric field is increasing in density, thus the electric field is increasing in strength. The force on this particle is then got to be increasing, so that its acceleration must be increasing. The opposite is true over here. That means if it's decreasing in density, that means the electric field is decreasing in strength. That means the force on it is going to be decreasing. Okay, and then that means that acceleration vector is decreasing as well. And so I imagine this should be slowing down. In between speeding up and slowing down, something has to change. And this has to be, at some point, it has to hit a constant speed. That only happens at interchange between speeding up and slowing down. So I'm imagining at B, it's got to be hitting a constant speed, because it's that interchange between going from speeding up to going to slowing down. Okay? All right. Hopefully that made sense with you guys. All right, let's try the right side. So over here you have the descriptions of what's going on, but you're supposed to then write the electric field, okay? So if this thing is turning at a constant speed, let me think about this for a second. If this is turning at a constant speed, that means its velocity vector needs to be the same. Constant speed means the velocity, the size, the magnitude of the velocity vector has to be the same size at each one of these points and add a tangent to that. So I'm drawing little velocity vectors to help me reason through this, right? And so this is kind of like a car turning in a circle. If the velocity vectors are pointed kind of at tangents to the circles, for it to keep turning, it has to be accelerating towards the center of that circle, okay? And so the acceleration vectors have to be pointed at 90-degree angles to those velocity vectors, okay, at each one of those points, okay? What that means is that this negative particle, that the force vectors have to also be pointed towards the center of that circle. And in a way, it's like a centripetal acceleration too. So those force vectors have to be pointed towards the center of that circle. Well, negative particles do the opposite of what the electric field is. So positive particles would be moving, accelerating in the direction of the electric field. Negative particles are accelerating opposite the direction of the electric field, which means the electric field has to be pointed outwards here, and outwards here, opposite direction of those force vectors. So what this must mean is that the center of this is an outwardly pointed electric field in all directions, and the only thing that could cause that would be a positive particle. So at the center of this, right here, has to be a positive particle, creating this electric field pointing outwards in all directions. So this is the electric field pointing out in all directions. All right. Well, there you go. And that's how to do the lab, the 2 pages in the lab. And then, so this is the first page in the lab. And this is the second page in that second lab. This first part is just 1 page, and it's a tutorial. Okay. The last thing to talk about is how do you apply. We talked a little bit in the last chapter about electric dipole moment, right? So P is the electric dipole moment. So P is the electric dipole moment. And we talked about a little bit about that dipole moment is based on the charge. It's the product of the 2 charges. So you multiply the 2 charges together. And separated by the distance d. Okay. And so what you have is you have this electric dipole moment that you're multiplying by the product of the charges and their separation distance, and that separation distance would be in nanometers. And so by using that dipole moment, and multiplying it by the electric field, you could actually calculate the overall torque that's going to be spinning. It's going to cause it to spin with, right? So suppose you had an electric field just pointed to the right, okay? And that would then create, and you have a charge, you have a positive charge on top right and a negative charge on bottom right. You would have a force that would be pulling, well, it would actually, this electric field would be pulling the positive charge in that direction while trying to pull the negative charge in that direction, which would cause it to momentarily spin and turn clockwise. So by taking that dipole moment and multiplying it simply by the electric field, you could see the overall torque acting on it. And again, that's just charge times their separation distance, and separation distance would be the distance between the negative and positive charge. And assuming both are the same charges, you just, it would be the QD on one side of those, right? So that gives you the overall torque, right? Which then you could use to find work and also electric potential energy. We're going to do the work and electric potential energy a different way by using energy and voltage later on in the next chapter of this. But I wanted to point this out. So that's what you're doing when you're placing a dipole in an electric field. The whole point is actually to get a torque, is to find how much it's spinning so much, and then you could then see the energy coming off that, which is then would be work that would be causing work on that field, or work on that to spin it, which is then a potential energy. Okay, so I wanted to just touch on that, and that's what is how this is linked to chemistry. Okay. Well, I hope you enjoyed this last part to calculating electric fields due to point charges. We're going to be then in the next chapter, which is a whole different module I have set up. We're going to be applying calculus, and suppose you're given a line of charge. So when we're talking about those lines of charges, how do you get the electric field due to billions of charges? Well, you have to use calculus to do that part, right? So if you want to get the electric field here and you just had a plate of positive charges, how do you calculate the electric field at that point due to billions of charges? Well, we're going to do that in the next part using calculus. All right? Well, I hope you enjoyed this part 2.3. Thank you.